Hello and welcome back to the Science of Concrete Materials class. This is lecture number 11 of the class, and today's topic is the development of the microstructure. We have just looked at the properties of the individual hydration products of the cement paste. And before we continue in studying the properties of the hydrated cement paste as a whole, we need to look at the mechanism of the development of the microstructure to gain more appreciation of how these products fit together. The microstructure comprises the solids, which is, the four compounds discussed just previously, in addition to the unhydrated residue, as you can see on the slide, the voids and the water present in the voids, which will also have a major impact on the behavior of the hydrated paste. We have to keep in mind that the hydrated cement paste is the heterogeneous material, and that of course will have major impact on its properties. If let's look at the how the microstructure develops first. This slide here, I've shown it before. I'm just showing it as a refresher, as a reference to what we are talking about. The solids, here are the voids, and the water present in the voids. That's going to be the focus of our discussion today. If the hydration mechanism and exact time and reasons for the formation of the hydration products is still the subject of debate amongst researchers. However, what is presented here is somewhat the widely accepted theories, and it is based on SEM, scanning electron microscopy, observation, and the help of other techniques such as the heat of hydration, calorimetry, and others. This approach, though, still assumes that the hydration is uniform around the cement grain, despite some evidence to the contrary. Also, as I mentioned previously, there is still a debate regarding the mechanism of hydration and why the formation of phases stops and starts again. Is it due to the formation of the barrier that breaks down, as we discussed before, or due to the ion concentration in the solution, or why the reaction does slow down in stage 5 or stage 4? Is it due to the availability of space, or is it due to the diffusion control reaction? Anyway, these questions, as I have discussed before, and as I said, the theories presented here are what reported in many of the textbooks. A schematic is shown here. This is idealized and simplified approach, which this is a proposed model of what goes on when the cement is mixed with water. When the Portland cement is dispersed in water, the calcium sulfate and the high temperature compounds of calcium begin to go into solution, and the liquid phase gets rapidly saturated with various ionic species as a result of the interaction between the calcium sulfate, the aluminate, and the hydroxyl ions. Within a few minutes of the cement hydration, the needle-shaped crystals of calcium trisulfo-aluminate hydrate, which we refer to as ettringite, first make their appearance, as you can see here. A few hours later, large prismatic crystals of calcium hydroxide and very small fibrous crystals of calcium silicate hydrates begin to fill the empty space formerly occupied by water. and the dissolvent cement particles. As you can see here, this is the calcium silicate hydrate. These are the ettringite needles, calcium hydroxide, and as you can see here, the hydration product, the calcium silicate hydrates, grows around the grains of the cement. After some days, depending on the alumina to sulfate ratio of the Portland cement, ettringite may become unstable and will decompose to form the monosulfoaluminate hydrate phase, as you can see here, which has hexagonal plate morphology. The hexagonal plate morphology is also the characteristic of calcium aluminate hydrates that are formed in the hydrated pastes, of either undersulfated or high C3A Portland cements. Okay. A model of the essential phases present in the microstructure of a well-hydrated Portland cement is shown here on this figure. And as you can see, the A here represents, the aggregation of the poorly crystalline calcium silicate hydrate particles, which have at least one colloidal dimension of 1 to 100 nanometers. The interparticle spacing within an aggregation is between 0.5 to 3 nanometers, an average of 1.5 nanometers. The H here represents the hexagonal crystalline products, such as the calcium hydroxide, the calcium alumina hydrate phases, and the calcium aluminate sulfate hydrate phases, or any form of this. They form large crystals, typically 1 micrometer wide. The C here represents the capillary cavities or voids which exist when the spaces originally occupied with water do not get completely filled with the hydration products of the cement. The size of the capillary voids ranges from 10 nanometers to 1 micrometer, but in well-hydrated pastes with low water cement ratio, they are less than 100 nanometers. So from this model I have just shown, it may be noted that the various phases are neither uniformly distributed nor they are uniform in size and morphology. In solids, we have to just remember this. In solids, the microstructural inhomogeneities can lead to serious effects on the strength and other related mechanical properties, because these properties are controlled by the microstructural extremes, not by the average microstructure. So, which, may look homogeneous and isotropic at the microstructure level. So as we said, it's a heterogeneous material. At the microscopic level, to the unaided eye, it might look uniform and homogeneous, but it's not. And the properties are controlled by the microstructural extremes, not by the average microstructure, which may look homogeneous. So, in addition to the evolution of the microstructure as a result of the chemical changes which occur after the cement comes in contact with water, attention has to be paid to certain rheological properties of the freshly mixed cement paste that also influence the microstructure of the hardened paste. So, for example, as will be discussed later, the anhydrous particles of the cement have a tendency to attract each other and form flocks, which entrap large quantities of mixing water. So obviously, their local variations in water-cement ratio would be the primary source of the evolution of the heterogeneous microstructure. with a highly fluctuated cement paste system, not only the size and shape of the pores, but also the crystalline products of the hydration would be different when compared to a well-dispersed system. So as our goal is to produce a uniform, refined structure, the use of certain chemical and mineral admixtures, otherwise known as the supplementary cementitious materials, slag, fly ash, silica fumes, these admixtures will help us achieve this objective, as we will see later. These are, examples that will help the rheological properties and remove calcium hydroxide from the microstructure, which would be harmful, as we discussed previously. So also, well-balanced aluminate sulfate ratios will also ensure that hydration products susceptible to sulfate attack are not present. So basically, the densely packed microstructure will improve its durability. So the rheological, other than the chemical reactions, the chemical changes that take place, we have to be aware of the other physical aspects, especially the rheological properties, and we make sure we have a uniformly uniformly dense or densely packed microstructure to make sure we remove the potential of the microstructural extremes from the hydrated cement paste. This schematic after Professor Scrivener, which shows the possible theory of development of the microstructure. I talked about this during the hydration lecture, so you could refer back to it. These slides here, the next 5 slides, also show a proposed schematic of the formation of the hydration products with time. These theories here are basically consistent. Let me go back here. They are consistent with the hypothesis, based on the calorimetry curve, which I have shown earlier. So as you can see, this is at 0 minutes. This one at 30 minutes. You could see what happened. The porosity start to go down. We have the first hydration product, calcium hydroxide and the ettringite. Then at 6 hours, the calcium silicate hydrate is there, ettringite is still there, calcium hydroxide also still there, and the porosity is increasing because the space occupied by water now is beginning to be occupied by the hydration products. And again, as time goes on, we'll see the porosity goes down and we have more hydration products. The calcium silicate hydrate increases, ettringite increased here, calcium hydroxide as well. And we see here other hydration products, the calcium aluminate ferrite hydrate or variation thereof start to appear. And again here, ultimately you will see calcium silicate hydrate, the most abundant phase. Porosity goes down considerably. Hydration products, completely formed. Calcium hydroxide, other hydration products, the monosulfate phase, which one coincides with the decrease in ettringite because ettringite converts to this phase, as we discussed before. So, the types, amounts, and characteristics, of the 4 principal solid phases in the hydrated cement paste, which these hydrated, the 4 phases, 4 solid phases in the hydrated paste, that can be resolved by an electron microscope, which we discussed earlier, those products. In addition, there to the remaining unhydrated cement paste, those we discussed before. Now, depending on the particle size distribution of the anhydrous cement and the degree of hydration, some unhydrated clinker grains may be found in the microstructure of the hydrated cement paste, even long after hydration. As stated earlier, if you remember, the clinker particles in modern cements generally conform to the size range of from 1 to 50 micrometers. With the progress of the hydration process, the smaller particles dissolve first and disappear from the system. Then the larger particles become smaller. Because of the limited space, available between the particles, the hydration products tend to crystallize in close proximity to the hydrating clinker particles, which gives the appearance of a coating formation around them, as I have shown just now. At later ages, due to the lack of available space, the in situ hydration of the clinker particles results in the formation of very dense hydration product, the morphology of which may resemble the original clinker. This is about the unhydrated cement paste. Okay, so let's talk about porosity. And of course, as seen from the above schematics, pores also form as a result of the hydration, and these pores are a major component of the microstructure. As we have been emphasizing the decrease in the capillary porosity during hydration, as can be seen, by the scanning electron microscopy observations. But pore size distribution is also of importance. But measurement of and classification of the pore sizes is complicated, basically by experimental difficulties and the interpretation. So there are two main problems. First, the paste must be dried in order to make the measurements, and drying almost certainly changes the pore structure. I will show the drying methods we talk about in the next slide. Second, a definite geometrical shape of the pores must be assumed in order to do these calculations. While the SEM, the scanning electron microscope micrographs show the pores to form a network of very irregularly shaped spaces, nevertheless a useful assessment of pore structure can be obtained. So how we measure pores? There are two main methods that are used to measure the pore size distribution of the hardened cement paste. Mercury intrusion porosimetry and the physical adsorption of gases. The mercury porosimetry involves forcing mercury into the pore system of the paste by application of external pressure. So that's the term intrusion. Mercury does not wet the paste, and force is needed to overcome the surface effects. The pressure required is inversely proportional to the pore radius. In the adsorption method, pores are filled by a condensing vapor gas through capillary condensation, which is a spontaneous process controlled by the surface forces. These are the methods used for drying the specimens. The de-drying, this happens at ambient temperature, but it requires a vacuum over dry ice. Oven drying, which is basically heating at ambient pressure to 105 degrees. The solvent replacement happens at ambient temperature, and this one involves soaking in methanol or isopropanol for several days. Okay, so let's say again, we're talking about pores and pore measurement, pore size distribution. Let's just have an introduction for the pores and voids, and what is their implication on the properties. Porosity increases with the increase in water cement ratio, and decrease with the decrease in water cement ratio. And also decreases with the increased degree of hydration. So means curing is of critical importance. Also, porosity increases. As porosity increases, strength decreases, and the permeability coefficient also increases. We will talk about permeability in a bit. So although in general, porosity does not mean permeability, the permeability and permeability coefficient depends on the connectivity of the pores, not just the presence of the pores. So there is distinction between porosity and permeability. Okay, so let's see how the capillary porosity is affected. Capillary porosity results, from the excess water used, basically for economy and workability. If you as we will see later, I mean, we use certain water cement ratio for mixture, and there is always excess water beyond what's needed for the development of the microstructure. So the capillary porosity results from this excess water. As water cement ratio or water cementitious material ratio, we're going to get used to this term in a bit after we talk about supplementary cementitious material. So the water to cement or cementitious material ratio, as it increases, the capillary porosity increases. Of course, I mean, this is for complete hydration. Also, we talked about the water cement ratio impact. We're talking about now the degree of hydration. The volume of capillary porosity in concrete is also related to the degree of hydration. Degree of hydration, keep in mind, is affected by curing, time, temperature, and the relative humidity. But as you can see here, as the degree of hydration increases, the capillary porosity decreases. Okay. As this is shown here, curing time in days. So as we increase the hydration, capillary porosity. So well-designed mix, proper curing will ensure that our concrete is durable. One thing here I like to show, which is basically the implication of the voids on strength and its relation to permeability. So the presence of voids affects the strength. Of course, the stress distribution concentrations within the matrix, permeability, and eventually freeze and thaw resistance, as we will see later. These pores, if no mitigation action is taken in freezing environment, will have major impact on durability of concrete. As you can see here, as the permeability increases, here's the capillary porosity percent by volume, and here's the permeability coefficient. As it increases, permeability coefficient increases. The strength decreases. So there is an inverse relationship that has been established between the strength and the porosity. Okay, this is a constant. We may talk about this later, but just what I want to show you to appreciate the fact, as porosity increases, the strength decreases. So let's talk about the concept of permeability. As we can see here, capillary porosity, as I said, which is a function of water cement ratio and degree of hydration, it's an important factor for determining the permeability of the paste. Large capillary pores, the macropores, control the transport of water or dissolved ions through the paste. So well-hydrated paste with low water cement ratios have permeabilities that may be more than 3 orders of magnitude lower than a paste with high water cement ratio. So that will give you really an appreciation of the impact of high water cement ratio. This is because the larger pores in lower cement ratio become isolated. Remember this. And the movement and the water movement is controlled by the flow through the gel pores, not the capillary pores, because the larger pores become isolated. Through these pores, it proceeds only with difficulty. So when we have low water cement ratio, the water movement will be controlled by the flow through the gel pores, which will be difficult. Computer simulations have show that when the total capillary porosity falls below 20%, as you can see in this figure here, the pores become disconnected, as shown here. So basically, if you look at these graphs, I'll talk about them. This one is a graph between the degree of hydration and the fraction connected for various water cement ratio. So as we decrease the water cement ratio, the fraction, for all degree of hydrations, the fraction of the pores connected becomes lower, as you can see. Okay, for each one. Now look at this curve, here. For the various water cement ratio, they're all collapsed together, and we are talking about measuring capillary porosity versus the fraction connected. When the capillary porosity falls below 20%, the pores become disconnected, and that means the concrete is not permeable. So let's just talk about this concept here, about porous and permeable. This one shows a material right here, which is non-porous and non-permeable. There's no pores exist within the structure, and of course it's not permeable, totally in contact. This one, porous but non-permeable. You see pores, but the pores are not connected, so they will not allow the movement of water through these pores. This one is porous and permeable. Pores exist and they are connected, so the water will move through them. Okay. Okay, so let's really talk more about the sizes of the pores. This slide here is shown here to give you a sense of the sizes of the hydration products and the voids within the paste the microstructure, and shows the typical size of sizes of both the solid phases and the voids in hydrated cement paste, as you can see. For example, let's see. For example, here is the interparticle spacing between the calcium silicate hydrate. See, it's on the order of 1 nanometer, and you see the capillary voids. Look at the size here to the size here. This is 100 nanometer. This is 1 to 10 nanometer. This is here where the size of the hexagonal crystal, the calcium hydroxide, or the low sulfate in the cement paste. Okay. As you can see, this is on the order of 1000 nanometer, 1 micrometer, as compare this to these. This one here, it shows, for example, the entrained air bubbles. These the air bubbles we forced to create within the concrete. Look at this, we're talking about 10 to the power 5 nanometers. This is the entrapped air, which incidentally get mixed with the concrete during mixing. So this gives you really a sense of the size. I mean, look at the variation of the size between this and this right here. A classification of the porosity in cement pastes is shown here in this table. You know, it can be seen there is an enormous range of pore sizes from, you know, 10 micrometers to less than 0.5 nanometers. Okay, as you can see. This means that the water that occupies the pores play many different roles. So it is useful to make a distinction between the capillary pores and the gel pores, okay, in the hydrated cement paste. The capillary pores are basically, as I said, the remnants of the water-filled space that exists between the partially hydrated cement grains. The gel porosity is regarded as an intrinsic part of the calcium silicate hydrate. The porosity seen in scanning electron microscope micrographs is the capillary porosity. The gel porosity cannot be resolved by the SEM and is included basically in the volume occupied by the calcium silicate hydrate. In mature pastes, the bulk of the porosity resides within the calcium silicate hydrate. Keep in mind the size division between capillary and large porosity. So if you look at this classification right here, so the division between the capillary and gel porosity is to a large extent arbitrary, because the spectrum of the pore is basically continuous. So it should be noted that the gel pores include small capillary pores. If we use the more accurate definition, that a capillary pore is one in which, remember this, a capillary pore is one in which capillarity effects can occur. That means meniscus can form. However, the capillary pore system is an interconnected network of pores through which bulk water flow and ionic diffusion occur relatively easily. That's the definition of capillary porosity. So look at these here and these sizes. I will talk about them toward the end of the lecture, but this is the classification of the pore sizes, hydrated cement paste. So as can be seen, you know, from you know the what's shown on this table here, you know, porosity over the whole size range of pores has an influence on the paste properties. Yet, as I said, it is difficult to get an exact assessment of the pore size distribution, because no one measurement encompasses the whole size range, and because it is difficult to interpret experimental data. So, comparison of porosity should be made with care. So just look at let me go back here. Look at these pores and the sizes. Just let me mention, you know, one more thing, you know, about the capillary, excuse me. The capillary voids are, as I said, irregular in shape. You know, the air voids are generally spherical, as this is just a comparison to give you a sense. A small amount of air usually gets, you know, trapped in the cement paste during concrete mixing. This is the entrapped air. You know, also for various reasons, admixtures may be added to concrete to entrain, you know, purposely tiny air voids. This is the entrained air. These voids may be as large as 3 millimeters. The entrained airs usually range from 50 to 200 microns, you know. So Both entrapped and entrained air voids in the hydrated cement paste are much bigger than the capillary voids and are capable of adversely affecting the strength. So keep that in mind. So let's look at the influence of the pore size on the properties of the hydrated paste, because this is really our ultimate goal, is to understand how to improve the durability. The macropores, these water in these pores behaves as bulk water. The properties affected, they affect permeability and diffusivity. The large mesopores, these are the roll of water, small surface tension forces generated. They affect permeability in the absence of the macropores. And also they impact shrinkage in the range above 80% relative humidity. The small mesopores, the role of water within these is large surface tension forces generated. They affect the shrinkage between 80% down to 50% relative humidity. The micropores, the water within them strongly absorbed water, no meniscus form, and these usually affect shrinkage at all relative humidity and also creep, as we will see when we study the dimensional stability of the concrete. So let's look at really a summary of the classification of the pores. First we have the calcium silicate hydrate interlayer space, as I said, between 0.5 to 2.5 nanometer in size. These are too small to adversely affect strength or permeability. These are independent of water cement ratio. Capillary pores, this one, they form in the space not taken up by the cement, and hydration products depend on water cement ratio. The size between 2.5 to 50 nanometers in well hydrated concrete or cement paste, irregular in shape. Size and amount is related to the water cement ratio and degree of hydration, as have shown in some of the graphs earlier. The micropores, generally these are less than 50 nanometers. They are more important for drying shrinkage and creep. And we have the macropores. These are larger than 50 nanometers. They are more significant for strength and permeability. We have the entrained air, spherical voids, 70 to 500 micron in size, added for freeze-thaw resistance. And we have the entrapped air, which irregular in shape and can be large. Pores larger than 2.5 nanometer may be filled with air, water, or pore solution, or a mixture. So this is just a summary of the pores and their implication. Okay, so let's see how we measure pores. There are two main methods that are used to measure the pore size distribution of hardened cement paste: mercury intrusion porosimetry and the physical absorption of gases, as I said before. The mercury porosimetry involves forcing mercury into the pore system of the paste by the application of external pressure. As I said, the mercury does not wet the paste, and force is needed to overcome the surface effects. The pressure required is inversely proportional to the pore radius of the paste. In the adsorption method, pores are filled by condensing gas through capillary condensation, as I said, which is a spontaneous process controlled by surface forces. Okay, but in general, the mercury porosimetry gives a better appreciation of the capillary pore system, while the adsorption studies give a better measure of the gel pore system, small mesopores and the micropores. The two methods, though, have overlap in size ranges, and they do not agree well. Because, first, the pastes, excuse me, pastes have to be strongly dried before measurements are made. Now, of course, physical changes in the calcium silicate hydrate affect the pore size distribution, particularly in the micro and mesopore range. Second, the two physical processes are quite different. Mercury must fill the pores from the outside by flowing through the pore system, so that the pore size distribution is really a profile of the size of the entries controlling access to pore volumes. This is, a percolation process and requires an interconnected network. The capillary condensation takes place simultaneously at all points in the paste where the required conditions are satisfied. So these are the differences. Third, a simple geometry must be assumed, although it is not the case as revealed by SEM. So you have to be aware of these limitations when reporting measurements or comparing measurements, okay? So let's just talk some more about the measurements and of the pore and the pore size distribution and their implication and their, what we can interpret from the results. These two figures here show a series of mercury porosimetry curves for pastes hydrated for different times and different water cement ratio. See, these are at different times, water cement ratio fixed. These are at one time, 28 days variance water cement ratio. Okay. By looking at the first figure, it can be seen that not only is the total volume of accessed pores is reduced, as you can see here, but also the fineness of the pore system increases. As you can see here, the entry from as the hydration continues, the entry, the threshold diameter decreases. So the volume of the macropores, meaning the volume of the macropores is rapidly reduced, but the distribution of the smaller pores is less affected. You see the similar trend observed in the second curve, where the water cement ratio is gradually reduced and measurements are made at the same degree of hydration, 28 days. The first inflection point, the threshold diameter, indicates basically the set of percolation, which is of course reduced with the reduced water cement ratio. The point of the steepest slope that represents the mean size of pore entry, ways that allows maximum percolation throughout the pore system. This is called the continuous or critical pore diameter. Okay. So as we see, basically the reducing the water cement ratio and increasing the hydration basically results in a finer structure and reduce the porosity. That's really what you need to get out of this introduction. So let's look at the, as we said, we have the voids and we have the water inside the voids. So let's look at really water in the hydrated cement paste, and let's look at a background. The water, the ratio of the mass of water to mass of the cement in a mixture is the water cement ratio. Of course, when SEMs are used, this becomes the water to cementitious materials ratio, as I mentioned. The water cement ratio, or the water to cementitious materials ratio, may range from 2 to 0.2 to 0.8. But typically, between 0.4 to 0.6. So water is introduced to the concrete urine mixin. It is necessary for reaction of the cement and the SEMs. It permeates the concrete urine service rather, I'm sorry. So because the water in concrete contains ion, it is usually called pore solution, and it has a high pH, as we indicated before, and this is a good thing in many respects, as you will see later. So let's talk more about the pore solution. The fluid contained in the capillary pores is not pure water, but an ionic solution that is in equilibrium with the hydrated paste. This is here a figure. It shows the ion concentration as time goes on. Its composition, this pore solution, its composition can be determined, by squeezing fluid out of the paste under high confined pressure. I have done that, and it's a very interesting process. And it gives a lot of wealth of information about the ions and ions concentration. The solution in the paste made with, for example, the solution in the paste made with pure calcium silicates is essentially saturated calcium hydroxide, approximately 1.2 gram per liter or 0.02 molar, with pH higher than 12. In cement paste, the solution chemistry is altered by the presence of the gypsum and the soluble alkalis. In particular, when potassium sulfate, which is very soluble, the arcanite, when this is present, the ionic concentration really extremely altered. As you can see here on the figure, it shows concentration of the calcium remains for extended time. This is the concentration of the calcium hydroxide, or the hydroxyl ions rather, and the calcium ions, concentration goes down. The sodium, it depends. It's less soluble than potassium, and it depends what form of alkali is present. Okay, so at the end of the induction period, calculations have indicated that maximum saturation with respect to calcium hydroxide is still achieved. Once the sulfate is fully consumed by the formation of yttringite, the pore solution is a solution of alkali hydroxide whose concentration is controlled by the alkali content of the cement. Okay, so this is just to have just a quick refresher of water and where water goes after hydration. So what is, the water in the voids impact on the paste, on the structure of the paste? Under electron microscopic examination, voids in the hydrated cement paste appear to be empty. This is because the specimen preparation techniques call for drying the specimen under high vacuum. But depending on the environmental humidity and the porosity of the paste, the untreated cement paste is capable of holding a large amount of water. Like the solid and the void phases discussed above, water can exist in the hydrated cement paste in many forms. So the classification of the water into several types is based on the degree of difficulty or ease with which the water can be removed from the hydrated cement paste. As there is a continuous loss of water from a saturated cement paste when the relative humidity of the environment is reduced, as we mentioned just a bit ago. The dividing line between the different states of water is not rigid, and there could be some arbitrary interpretations. In spite of this, the classification this classification is useful for understanding the properties of the hydrated cement paste. In addition to vapor in empty or partially filled voids, water exists in the hydrated cement paste. And if you remember, I have shown this slide before, and we have shown, where the bulk water exists. For example, as in the capillary pores here, we have these water molecules in the micropores, or physically absorbed in external surfaces under, surface forces, but mobile. And this is the water in very small micropores between calcium silicate layer, the calcium and silica layers, or called interlayer water molecules, which located at special sites in the internal surface between the layers, but not very mobile. So we talked about this before, so let's continue. The capillary water present in voids larger than 2.5 nanometers. In capillaries larger than 50 nanometer, water exists as free water because its removal does not cause volume changes. Remember this. In capillaries 2.5 to 50 nanometer, removal of water results in shrinkage because new bonds can form between the calcium and silica, the CEO, SiO2 surfaces, these layers. Okay. The adsorbed water, which is the water physically adsorbed to the solid surface in the calcium silicate hydrate, this one can be removed on drying to relative humidity around 30%, which result in shrinkage then. The interlayer water, the water associated with the calcium silicate hydrate structure, can be removed only on strong drying, right down to almost 11% relative humidity, which will result in shrinkage. And we have the chemically combined water. This water is an integral part of the various hydration products. This one only lost on decomposition during heating. Okay, so these are the various states of water and how the water exists in the microstructure of the paste. This one here, an SEM micrograph. It shows, for example, the calcium silicate hydrate, the capillary pores, for example. These are the gel pores. This is calcium silicate hydrate gel. These are the gel pores. And of course, in addition to the other various products like the ettringite needles, you can see here the monosulfoaluminate. You can see here, this one that's not clear what this appears to be, but maybe a calcium hydroxide grain, nonetheless. But this one, on a graph, it shows the pores and the gel pores, the capillary pores and the gel pores. Okay, I know we have discussed many things in this lecture, so let me just try to summarize and recap quickly what we talked about. So the microstructure comprises solids, voids, and water. The solids, calcium silicate hydrate, 50 to 60% of the volume of the paste, responsible for strength. Calcium silicate hydrate, 20 to 25% of the volume, works as a buffer to keep pH high. It has major drawbacks in durability, carbonation, and acid attacks. Talked about the sulfoaluminate phases, 10 to 15% of the volume. Major drawbacks are the durability to sulfate attack. We have the unhydrated residue, the cement residue, about 5% of the volume. The voids, we have the capillary pores, which they impact permeability and diffusivity, dry and shrinkage at high relative humidity. We have the gel pores. This one impacts drying shrinkage at lower humidity and creep. We have the, and again, just to repeat, the capillary pores, as I said, have impact on strength and permeability. The gel pores, we have the air voids, which are the entrained air, air voids we intentionally add to the concrete for freeze-thaw resistance, and we have the entrapped air. Okay, so we also learned that capillary pores larger than 50 nanometer, about the water, where it exists in capillary pores larger than 50 nanometer. Its removal, does not impact drying shrinkage. The capillary pores 2.5 to 50 nanometer, and again, impacted drying shrinkage at low relative humidity and creep. We have the adsorbed water, its removal results in shrinkage. Interlayer water, its removal results in shrinkage. The chemically combined water lost only on decomposition during heating. So this is just the highlights, as I said, of the voids in water. And by this we come to the end of lecture 11 about the microstructure, the voids and the water within the voids. Next time we will talk about the calculations of the volume changes of the hydrating paste, solids and volumes. So thank you for watching, and I will see you next lecture. Thanks.